So for the final part of the introduction, I would like to talk about the CAP theorem, or Brewer's theorem. The CAP theorem is one of a number of theorems that exist within distributed systems, but it's a very practical theorem, and it concerns with the practical limits that can be placed upon distributed data stores. Distributed data stores are systems that store data in a decentralized way. Examples of distributed data stores include distributed file systems and distributed databases. Typically, these systems consist of multiple nodes. So in a file system, you have multiple file system nodes, and in a distributed system, in a distributed databases model, you might have multiple database management systems. And essentially, distributed data stores are concerned with how to store the data in a reliable, secure way. And that typically involves making multiple copies of the data, we call these copies replicas, that are distributed across some or all of the nodes. In a file system, it would typically be some of the nodes, so you have a copy of the file on multiple different servers. In a distributed database, it will typically be all of the nodes. In a distributed database, each node would be a copy of the database, and the idea is that you apply a policy that means that all of the database instances get updated so that you have a consistent view of the data. And when I talk about distributed databases, by the way, I'm talking in a very general sense, so it could be an SQL database or it could be a NoSQL database. In fact, this model applies to all types of data stores. So typically, there are three main approaches to managing the update of these replicas of data. One approach is known as the passive approach, which is the one you see down here, and this approach adopts a master-slave configuration, or a primary-secondary configuration. And in that model, the client interacts with a single node in the network, which is designated the master node, and the master then is responsible for updating the slaves. Depending on the particular model used, it could be the master talks to the slave, which talks to the slave, or it could be the master talks to all of the slaves at the same time. A second type of model is called the active model, and this model is a decentralized solution, and this solution, whenever the client performs an update of the database or the distributed file system, it contacts all of the nodes in that distributed file system and updates them all at the same time. These types of systems generally work by saying that if you've got n nodes and you require that you set some threshold t, which is a minimum number of nodes you need a response from, and when you get updates from t of the n nodes, you then consider your data to be updated. So t might be a threshold set based on something like a Byzantine something related to the level of fault tolerance you want to provide within the system. So the more fault tolerant you want, the more replicas you want to be updated before you consider the update complete. The third model then is called the lazy or gossiping model, and this is a more recent model that was developed. The lazy model is a variation of the active model, where the active model accepts a minimum number of updates performs a minimum number of updates before it considers the replicas to have been updated, but then allows for some back-end propagation of data between the individual nodes, so they can essentially up to date, so that those nodes that are out of date can obtain up-to-date information from nodes that were up to date. And it's this behind-the-scenes interaction that is the gossiping part of the architecture, that they interact to get updates from between each other behind the scenes, while the main client is requesting updates. And we call these things the clients, but this could be itself could be a server as part of a bigger system, and it's just the front end of the system that is interacting with the back end replicas. This could be itself be a node within a bigger system. The key issue anyway that's faced by all of these approaches is how to update. How up to date does a read have to be? So if I perform an update in this model, because everything goes through the master, when I do a read, I also read through the master, which means I get the up-to-date value. In this model, I perform an update, a write, then only some of these nodes will be updated. So when I perform a read, again a multicast model is used, Therefore, one of the node that replies at any particular the node that replies to a read may or may not be a node that was updated by the last write, in which case the client may receive an out-of-date record, at which point it can say, well, that's out of date, therefore therefore it could potentially return an out-of-date value. The idea of the lazy model is that whilst some of the nodes will be out of date, the hope is that behind the scenes the nodes will update themselves so that it's more likely that when you do your multicast read, you get back an up-to-date version of the data, of the record. So the Brewer's theorem, or the CAP theorem, says that when you design these distributed data stores, it's impossible to satisfy the three following guarantees. It's impossible to satisfy that a system be both consistent, available, and tolerant to partitions, and partition tolerant. The first guarantee refers to the fact that whenever you perform a read, a distributed data store has to return the most recent write, and if it doesn't return the most recent write, it returns an error. The second guarantee says every request must receive a non-error response, without guarantee that it contains the most recent write. So these two are quite contradictory. So consistency says you must be the most up-to-date write, or you give an error. Availability says you must give a response, but it doesn't have to be the most recent value. And that's the trade-off that the CAP theorem talks about. The third guarantee, which is partition tolerance, is that the system should continue to operate despite an arbitrary number of messages being dropped. So if we go back and look at our systems, if we think about this system here, then any of the updates to the replicas can fail, and this system will give you always the most recent write, because there's a single centralized component that is the master, and the master will always be updated and will return the most up-to-date value. In this model here, the active and the lazy models, there is a possibility that one of the nodes will return an out-of-date bit of data. If one of the writes failed, then one of the nodes might return an out-of-date response, which would then cause the consistency model to fail, or consistency guarantee to be failed, but would satisfy the availability. So some of these models are more oriented towards consistency-based systems, and other models are more oriented towards availability-type systems. In general, when you think about it from the databases perspective, SQL databases are designed to support consistency over availability, and that's because they support this ACID transactions model for atomicity, consistency, isolation, and durability. In contrast, NoSQL databases, one of the main motivations for them being developed was that they wanted to support availability over consistency. So basically available, soft state, and eventual consistency. And this was the choice that people were given with the development of NoSQL databases. And they grew out of a recognition that SQL databases, with their stronger requirements for consistency, that this guarantee could not be broken, led to systems that were too brittle when considered and truly web-scale applications. And it's when you consider those really large-scale applications, consistency can become a millstone around your neck, because it requires really a more centralized model, and that more centralized model results in requirements that mean that have consequences for the performance and the responsiveness of a system. In general, there are many consistency models within replication systems. I'm going to talk only about two of them. One is the strict consistency model, which is the one that is most correctly satisfies the consistency guarantee. And strict consistency says that a write to a variable in a data store must be seen immediately by all nodes. And in practice, this sort of solution can only be achieved by centralized systems, or can only be achieved by centralized systems, and But sometimes it's necessary to have these more centralized systems, for example, banking systems. So if we want to consider things that solve this, it doesn't mean that it has to be a single database. What it means is that we need to go for this sort of passive model often. There is another type of consistency model called linearizability, which does offer a weaker form of consistency that would stand to the consistency guarantee, and it uses some sort of decentralized algorithm to ensure that when a write is done, all the nodes the write becomes visible on all the nodes at as close as possible at the same time. Okay. The alternative to strict consistency that deals with the availability that is more supportive of availability is eventual consistency. Eventual consistency says that reads eventually return the same value, but there is no guarantee that it's the latest write. So eventual consistency has a similar model of updates taking place within the system, but whilst the strict consistency and the consistency guarantee require that no read that reads return either failure or the latest value, eventual consistency allows for stale values to be returned. So you can have an older value returned even if a newer value has been written to the system, to the database. This sort of model works well when it's not strictly required in an application that every client see the updated write, see the most recent write immediately. An example where this sort of thing can be useful is things like tweeting in Twitter. Okay, this is where this sort of thing would be developed for. So in Twitter, when you tweet, you're basically writing a record to a database of some sort, a distributed database. That value is written to a type of database using either gossiping or active replication, with the idea that you write it to your local database, the one that your client is connected to, and the database is essentially the message, the update of that from that database is passed out slowly through the network of the distributed data store network, and eventually other nodes will all receive that update. And when they do, if you have a follower who's in a different country, potentially in a different location, who's connected to a different node in that distributed database, eventually they will receive the update and they will see your tweet. What's guaranteed is that you have consistency in the order in which the tweets from you are guaranteed. What may not be consistent in these sort of weaker consistency models is the interleaving of the tweets by you and the tweets for other people. So somebody may, if you got A, B, and C, and A, B, and C tweets at the same time, to some users you may see A followed by B followed by C. For other users, they may see B followed by A followed by C. Other users may be C, B, A. The ordering is not guaranteed because the ordering is essentially the three tweets are created in parallel and there is no ordering. There's no clear ordering between them. So what is ordering is that A's tweets are in order, B's tweets are in order, and C's tweets are in order. But the interleaving is not guaranteed. And this relates to some of the work that was done, which I don't really talk about in this thing. It relates to the issue of how you guarantee consistency or how you order writes and updates to data stores, distributed data stores, which is done through timestamps, and is typically supported through the use of logical clocks. These are things like Lamport happens before relation or vector clocks. Now, I say I'm not going to talk about all that stuff. It's all very important stuff to know. But what you'll find is that when you read some of the academic papers that I'm going to give out to you, when you have to review one of those academic papers, you're probably going to find people talking about consistency models. They're going to be talking about CAP Theorem. They're going to talk about replicas. And these concepts that I've talked about in this short presentation will all be trawled over in much greater detail, with much deeper analysis of the implication of those details or those constraints to the system being discussed. And that's really one of the reasons why I've talked about the CAP theorem here, because you're all going to probably have to understand that this is a key theorem of distributed systems when you go and read those papers. And it's a key theorem because what it does is it talks about the limits on the guarantees that can be given to how a distributed database will operate. Okay, so I'm finished talking about theory. I'm finished with my introductory material. What I'm going to do next is the next set of slides, I'm going to move on to talk about Maven. And on Wednesday we'll be doing the live lecture, and then after that I'll move on to talk about Docker. And on Wednesday I'll be giving you the walkthrough of Maven and Docker in the live stream. Okay.